Assalamu alaikum everyone. This is going to be a lecture about the acid-base principles. So just to start off with a couple of basics, okay? If you want to calculate the pH, the equation's right there. You do log 1 over the concentration of hydrogen, or you find the negative log of hydrogen. And you can see here that as the pH increases, you're going to get, as the pH decreases, you're going to get an exponential increase in the concentration of hydrogen, right? This is because, this is basically just by nature because it's a log graph. One important thing that this means is that we need to have a very, very tight control over the equilibrium, because even small changes like 0.1 on the pH scale make a big, big difference, right? And the more acidic you get, the bigger the difference it makes in terms of hydrogen. There are two main organs that help us regulate the concentration of hydrogen, being the kidneys and the lungs. Now, the lungs, as I'm sure you already know, regulate the pH through ventilating CO2, getting rid of CO2. And then you have the kidneys, which can secrete hydrogen and reabsorb bicarbonate, and thereby controlling the concentration of hydrogen. Okay? Now, there is an equation which I'm not really going to get into, which is the Henderson-Hasselbalch equation. That's more important for your simile, which is why I'm not really going to get into it here. I didn't really see it much mentioned in the lecture. But basically what it will tell you is that you have hydrogen on one side and CO2 on the other. Oh, no, sorry. So the basic idea is if I just get out the pen. Which for some reason isn't working. Okay, that's 1 second. Okay, now that we're back from technical difficulties, the basic idea is that you have CO2 and water on one side, and then on the other side we have HCO3 and hydrogen. Okay, and as the concentrations on each side go up, that's going to push the equation towards the other side. So as a quick example, if you hypoventilate, which would increase the amount of CO2, that's going to push the equation this way, which will increase the concentration of hydrogen, right? And vice versa, if you increase the concentration of bicarbonate, that's going to push the equation across, which will lower the concentration of hydrogen. And so this is the basic idea by which we regulate our hydrogen concentration, all right? And because this is renal, we're going to be mostly focused on the kidney's role. Okay, so here again is the equation that determines the control. Because the system always tries to stay in equilibrium, and just as a side note, because I didn't mention this earlier, we have an intermediate here, which is H2CO3. Okay, so increasing carbon dioxide pushes it this way, which then pushes it across, and vice versa for HCO3 minus. Okay, system will always try to stay in equilibrium, and like we said, as you increase one side, it will push it across to the other. Okay, so here's a quick illustration of a kidney that I drew earlier today. And so just to take you through the journey across the kidney and how each part will control the hydrogen concentration and therefore the acid-base equilibrium. Okay, so first of all, the proximal tubule, if we just zoom in here. Now, like this, it's a bit difficult to illustrate. So here's a different illustration that's a little bit better. Okay. First of all, the proximal tubule is going to be responsible for 80 to 85% of the regulation of bicarb. Okay, so bicarb is 80 to 85% regulated in the PCT. Now what it does is that in the lumen over here, you're going to have H plus and HCO3 minus, which is bicarb, they're going to combine together to H2CO3, like we saw in the equation, and then separate again into CO2 and water. All right? Now CO2, because it is non-polar, because it is hydrophobic, it can diffuse freely across the cell membrane, where it's going to go backwards across this same equation, right? So it'll go back into H2CO3, back into H+, and bicarb, and so we end up with HCO3, H+, and then this bicarbonate will go back, will go out into the interstitium and get reabsorbed. And the H+ can then go back out into the lumen through the Na plus H exchanger. And the enzyme that's going to regulate this process, okay, so on either side, we have here a carbonic anhydrase 2. So two, and on this side, carbonic anhydrase. Wait. Sorry, it's been a long day. On this side, it's carbonic anhydrase 4, and on the other side, it's carbonic anhydrase 2. And so this way we reabsorb bicarbonate and we take it into the lumen. All right? Now, one thing to note is because we have the NaH exchanger over here, if you have a state of hyponatremia, this exchange is going to be less effective, and so this whole process becomes just a little bit less effective. Okay? However, there is another port over here, which is just a hydrogen ATPase, which can also transport H+. All right? Now, the proximal tubule has one other function, which helps to regulate the hydrogen concentration, and that is it helps to produce ammonium. Okay, so this is ammoniogenesis. Now, the way it does this is that it's going to have a transporter over here on the interstitial side called SNAT3. This transporter is very important, and it's the one that's going to transport amino acids, especially glutamine, into the cell. Afterwards, it will go through a pretty long process that I'm not really going to get into much detail here. But what it's going to end up with is it's going to produce ammonia, which in the lumen will combine with hydrogen to produce ammonium. Now, what ammonium does is that because you have ammonia, which is taking up all of the H+ ions, the urine becomes less acidic. And this basically means that your kidneys aren't going to melt from all of the H+ ions that are in there. Okay? So, back to the kidney. Next, we're going to skip the loop of Henle, which doesn't really do that much, but one thing it does play a role in is it helps to recycle the ammonia and takes it back so it can be reused in the proximal tubule again. Okay, but onto the distal tubule. Very, very briefly, one thing the distal tubule has is it has an NaH exchanger, which helps to just secrete hydrogen into the urine, and it can help regulate the equilibrium that way. And that's roughly it. More importantly is you have the collecting duct. Now, once again, just to have a bit of a better diagram, here's a different illustration that I made. We have the principal cell over here. Now, the principal cell doesn't really do much that's important for our purposes today, but I just decided to include it because it does have a potassium port over here, a potassium channel, which moves potassium into the lumen. This is going to become important because in our alpha intercalated cell, what you have over here is a potassium hydrogen exchanger, okay, which is an ATPase. And through this, it'll move the hydrogen inside, which so by this process, it can move the hydrogen inside, which allows the wait, I am so lost. Ah, okay. All right. I was wondering why the diagram looked weird, and it's because I was reading it wrong. Yay. Point is, this is a H plus potassium exchanger. It moves the hydrogen out along with a second hydrogen ATPase, just like the one we saw in the proximal tubule. The main idea being is that we're going to get the same process here as we had in the proximal tubule, just on a lesser scale. So again, you have the H plus bicarb, which through carbonic anhydrase 4 are going to form CO2 and water, and then the CO2 moves in, carbonic anhydrase 2 activates again, so that's Ca2, which forms bicarb, which can then leave the cell through another channel. A similar thing happens with the beta intercalated cell, but this time the beta intercalated cell is going to be responsible for reabsorbing hydrogen into the blood. So a similar, so just to draw the channel here, this channel is a chloride bicarb exchanger. So it pulls in chloride and it releases bicarbonate. The beta intercalated cell is basically the exact opposite of the alpha intercalated cell. So these, so the ATPase and the potassium hydrogen exchanger are on this side, where they release it into the blood, and the, wait, I don't know if you can see my pointer well. But basically, these channels are on this side over here, and this channel is on this side. And so what it's doing is it's doing sort of the reverse process of the alpha intercalated cell, where it's going to reabsorb the hydrogen and release the bicarbonate into the urine. And so that's just the basic principle of how the kidneys play a role in regulating your acid-base status. Now, how do we diagnose acid-base disturbances? The first rule one that I want you to always bear in mind is that you always have to check the pH and the PCO2 first. Okay? Now you might be wondering, why am I telling you to check the PCO2 and not, say, the bicarb, for example? And that's because PCO2 is a very, it's a very acute system. Because the lungs, you can immediately just hyperventilate or hypoventilate. And so it will immediately tell you about the current respiratory status. And if you have a situation where you have a mixed disorder, where you have like metabolic acidosis and respiratory acidosis, that's fine. You'll still mention the respiratory acidosis first. Okay, so the general rule of thumb is if pH and PCO2 are going in the same direction, then it's a metabolic problem. If the pH is low and the PCO2 is low, then it's metabolic acidosis. If the pH is high and PCO2 is high, then it's metabolic alkalosis. If they're in the opposite direction, then it's a respiratory problem. So if pH is low, PCO2 is high, it's respiratory. pH is high, PCO2 is low, it's respiratory alkalosis. Okay? Now, part of the regulation is that for each of these situations, you're going to have compensation against them. Okay? So in the case of a in the case of a metabolic problem, let's talk about the metabolic ones first. what you're going to have is your body is going to change its ventilation. You're going to change your breathing pattern to try and either get rid of more PCO2 or try and keep more PCO2. Okay. So in the case of metabolic acidosis, you're going to hyperventilate. This will get rid of more PCO2 and it will lower the, this will get rid of more carbon dioxide, lowering the PCO2, which will try to bring the pH back up to normal levels. And the reverse happens with metabolic alkalosis, where your pH goes up, you'll slow down or you'll hypoventilate, which will lead to a higher PCO2, and it will try to bring the pH back down to a normal level. Okay. Now, for respiratory problems, so respiratory acidosis and respiratory alkalosis, it's a little bit different, and that's because we have an acute phase. So, an acute phase, and we have a chronic phase. Okay. Now, in the acute phase, this is an immediate response or a near immediate response that happens from within the cells, where the cells are going to release a bunch of buffers, right? So this could be buffers like phosphate and hemoglobin, and these will try to either hold on to the hydrogen in the case of respiratory acidosis, or in the case of respiratory alkalosis, these cells will take the buffers out of the blood, and so more hydrogen stays in the blood. Okay, and then we have chronic, which is sort of the delayed response. This is where your kidneys start to kick in and will try to secrete hydrogen and reabsorb bicarbonate to sort of regulate the levels. Okay, so let's talk about our first disorder for the day. Okay, so this is what I mentioned with compensation. The body doesn't like not having a normal pH. It doesn't like not having a pH of around 7.3 to 7.4, so 7.35 to 7.4. If you have metabolic acidosis, your body will compensate via hyperventilation, vice versa, where it'll hyperventilate. And then in respiratory acidosis, the delayed response, which is excreting more hydrogen, reabsorbing more bicarbonate. Okay, so first of all is metabolic acidosis. We have, like we said before, we have a low pH and a low PCO2. Now our first step is to find the anion gap. This is because you'll have two different disorders under metabolic acidosis, which is non-anion gap metabolic acidosis and high anion gap metabolic acidosis. This is how you find it with this equation. Okay, and we'll take an example in a short while. The anion gap tells you a little bit of information about what the underlying cause of acidosis could be. Okay, so these are some of the causes of non-anion gap metabolic acidosis. I'm not really going to go into much detail for this because it's quite literally just look at the acronym and then memorize the acronym. Okay, and at the same time, I did just steal the slide I just frankly stole the slide from the lecture, but this is what the doctor wants you to know, so keep this information in mind when you're going through the questions. And then we have high anion gap metabolic acidosis, which has these causes, so glycols, oxyproline. Again, I'm not really going to go into much detail. This is sort of a more read and memorize, and if they want you to go into more detail, they'll be talked about in other lectures, and so I'm not going to go into much detail here. Okay, so let's go through the formulas for metabolic acidosis. The first important one, which is the super high yield formula, is the Winter's formula, okay, which is PCO2 equals 1.5 times the bicarb then plus 8 and then plus and minus 2 to give you a range. Okay. So it's very easy for me to just tell you the equation and then be like, all right, let's move on. But just to elaborate very, very quickly, what we're going to do is we're going to first look at our concentration of bicarbonate, and then we want to try and find the expected compensation, like what we're expecting out of the body to compensate for the drop in bicarbonate, okay, in the case of acidosis. And so what you're going to do is you're going to basically put it into the equation, find the numbers, and then you'll get the expected carbon dioxide level in the blood. If the actual carbon dioxide level isn't within the range, then that means there's a second problem. So if it's the expected carbon dioxide is too high, then you have another, then other than the metabolic acidosis, you also have a respiratory acidosis. If the CO2 is too low, then on top of the metabolic acidosis, you have a respiratory alkalosis. Okay, now, like I said here, I have a couple of examples that I definitely did not steal from anywhere. Where is my mouse? Okay. So our first example, our patient has a pH of 7.2, a PCO2 of 22, and a HCO3 of 9. Okay, I'm not really going to go into much detail on the anion gap calculations for this particular example, because this is just more to focus on the Winters formula. Okay, so very quickly, the pH is low, so that means it's an acidosis, and the carbon dioxide is also low, right, which tells me that it's a respiratory acidosis. Okay. Sorry, it tells me that it's a metabolic acidosis. And again, just like sort of confirming it, our bicarbonate is high. So let's calculate what the, sorry, our bicarbonate is also low, which confirms that it's a metabolic acidosis. So let's calculate the expected compensation using Winter's formula. To do that, like we said, it's 1.5 times 9, okay, plus 8 plus minus 2. So 1.5 times 9 is 13.5, plus 8 is 21.5, plus minus 2. So 21.5 plus minus 2 gives us a range of 23.5 to 19.5. Okay, so 23.5 to 19.5. This is the range that we expect our PCO2 to fall in. And since in this case it does fall within the range, then we can say that this is a metabolic acidosis and the compensation is appropriate. Okay, now in our second example, we have a pH of 7.28, a PCO2 of 40, and a HCO3 of 12. Okay? So, again, applying Winter's formula, we have 1.5 times 12 plus 8 plus minus 2. So this is going to be 18, plus 8 is 26, plus minus 2, it gives us a range of 28, so 26 to 28. Okay, now quite obviously our PCO2 is not within that range, it's much, much higher. So since it's much higher, this tells us that we have an uncompensated metabolic acidosis with respiratory acidosis. Okay, because like we said, compensation is not appropriate, it's outside the range, and because the PCO2 is high, then it's a respiratory acidosis. Okay? Okay, so there's one more concept that I want to go over for when it comes to the metabolic acidosis, and that's delta delta. Okay, now delta delta sounds like it's a bit fancy, but I promise you it's very simple, and hopefully once we go through it, it'll be a bit more clear. Okay? And the way delta delta works is what you'll do is you'll take the anion gap, which, like we said, to find the anion gap, you take the sodium concentration, and then you add, nope, absolutely not. Take the sodium concentration, and then you subtract the chloride plus the bicarb, okay? To find the anion gap. And then to find the delta delta, what you do is you do the anion gap minus 12, and 12 is the normal anion gap, divided by 24 minus the bicarb level. 24 being the normal bicarb level. All right. Now, once you do this equation, you're going to get one of three results. Okay. In the first situation, the delta delta is less than 0.4. Okay. And without going into too much detail about the fancy maths, what this tells you is that it's a non-anion gap metabolic acidosis. Okay. Or ANAGMA. So non-anion gap metabolic acidosis. Now, in the second situation, your anion gap is between 0.4 to 2. In this case, what you have is a high anion gap metabolic acidosis, but no other disorder, okay? Because it's like not quite high enough to be another disorder, okay? Finally, if it's above 2, then first of all, you have a high anion gap metabolic acidosis. But the second thing is that you have above normal levels, like you have a high anion gap metabolic acidosis, and even before that metabolic acidosis, there was a very high level of bicarb. Now, in what situation can this happen? Well, for example, this can happen in a patient with chronic respiratory acidosis, where the kidneys are trying to reabsorb as much bicarb as possible. And so in this case, if you start to develop metabolic acidosis on top of it, then you're going to get a metabolic acidosis on top of a respiratory acidosis. Okay? But that's something you'd see in the compensation anyways. The other case where it can happen, and this is the sort of the more important one that I want you guys to focus on, which is if you have a pre-existing metabolic alkalosis and you started to develop a metabolic acidosis on top of that. And so the metabolic alkalosis is going to push the bicarb up very high. Okay? And then you develop the metabolic acidosis, and so it's going to cause it to drop a little bit, but it's also going to cause a very severe, but because the pH has gone down, the PCO2 is going to drop with it, which will produce the metabolic acidosis with a respiratory alkalosis, and then on top of that, you'll have a pre-existing metabolic alkalosis. This sounds really, really complicated, but hopefully I can break it down with an example, which will make it a bit more which will hopefully make it make a bit more sense. Okay, so let's take our example. So we have a patient that has a pH of 7.24. Okay. And on top of that, we have a PCO2 of 25. Okay, so immediately it's an acidosis, and because the PCO2 is low, so they're in the same direction, so you already know that it's going to be a metabolic acidosis, no matter what else I tell you. Okay? Now, bicarb in this example is 10. Okay? And to find the anion gap, we need sodium and chloride. And for this example, they are 140 and 100. Okay, so we have a metabolic acidosis. Like we said, we need to find the anion gap. That's going to be sodium, which is 140, minus bicarbonate, which is 10, plus chloride, which is 100. This gives us a result of 30. So this gives us a result of 30 for our anion gap. Now, the normal anion gap, like we said before, is supposed to be 12. And since it's much, much higher than 12, then you already know that we have a high anion gap metabolic acidosis. Let's find delta delta for this case. So first of all, you have the anion gap. Again, let me just draw the equation. Minus 12 over 24 minus the bicarb. Okay? In our patient, that's going to be 30 minus 12 over 24 minus 10. Okay? So 30 minus 12, that's going to be 18. 24 minus 10, that's going to be 14. All right? And the end result of this ratio, if I just do that, is going to be 1.2. Going to be 1.28. So like we said before, in this case, it's less than 2. It's between 0.4 to 2.0, which tells us that our case does have a high anion gap metabolic acidosis, but they don't have another disorder on top of it, right? Like they don't have a pre-existing metabolic alkalosis, whatever that means. Okay. Now, if we change up the case that we have just a little bit, okay. So, for example, let's just bump up the bicarb to 20. This will change. Wait, will it? Sorry, I'm sort of freestyling the numbers here. Okay, perfect. Now this will change. So again, instead of 10, it's now 20, which will make our anion gap into 20. Okay, this is still high since it's above 12. Let's apply the delta delta equation again. So we have 20 minus 12 over 24 minus the bicarb, which is 20. This gives us a result of 8 over 2 over 4, 8 over 4, which in terms of the delta delta gives us a result of 2. Now this is basically on the edge, like on the higher end, which tells us that most likely the patient, before developing their metabolic acidosis that they presented with, they probably already had a metabolic alkalosis from before. Okay? Now, just for the sake of the example, let's calculate if they have an appropriate compensation. Okay. So again, we have a pH 7.4, PCO2 25. In our second example, we said the bicarb was 20. Let's apply Winter's formula. Okay, so Winter's formula again is 1.5 times the bicarb, which is 20. So 1.5 times 20 plus 8 plus minus 2 to give us the range. So 1.5 times 20, this is 30, plus 8 becomes 38, plus minus 2 means our range is 36 to 40. Okay? Now, obviously, in this case, the compensation is inappropriate. And so what we will say is, in total, our patient has an uncompensated metabolic acidosis plus a respiratory acidosis okay, and like we said when we found the delta delta, they had a pre-existing metabolic alkalosis. So we have a third disorder as well in this case, which is a pre-existing metabolic alkalosis. Okay. All right, that was a terrible mouthful, but hopefully it was all clear. Just before we move on, does anyone have any questions? All right. So, the next case we're going to take is a metabolic alkalosis. All right. Now, unlike before, I'm not going to waste any time on the etiologies. So let's just jump right into the formula. Now, unfortunately, the formula for metabolic alkalosis does not have a fancy name. Like the Winter's formula, it's quite literally just called the compensation, right? The formula for compensation. Okay? And the way you find it is you have, it's not where I want to write. So the way you find it is delta PCO2, okay, is equal to 0.7 times delta HCO3. Okay, now all these delta signs mean is the difference between the concentration that we have and the normal. All right, so our expected change in PCO2 equals 0.7 times the expected change in bicarb. All right, let's take a quick example. So in our example, we have a patient that has a pH of 7.5, which is high. They have a PCO2 of 47, which is also high, and a bicarb of 34. Okay? Immediately, just from looking at the pH and the PCO2, we already know that this is going to be a metabolic alkalosis. Okay? And looking at the bicarb just sort of confirms that. All right? Now, to find what our compensation should be, what we're going to do is first is we are going to take our HCO3, then we are going to do 24, which is normal, which is the normal bicarb level, minus 34. Okay? Now this equals -10, but for the sake of this equation, you can just ignore the negative here. Right? Since it's just the delta, it's the change. All right? So 0.7 times 10 gives us our expected change in PCO2 of 7. All right? So that means our expected level of PCO2 should be 40, which is the normal PCO2 level, plus 7, which gives us a PCO2 level of 47. All right? Now, normally you take this range, you do like a plus minus 2, just to give a sort of range of where it can be. So in this case, our range is going to be 45 to 49, but as you can see here, the PCO2 was dead on the exact amount that it needed. All right? So that's the equation for metabolic alkalosis. Does anyone have any questions about that? Okay, all clear. All right. So let's move on to the respiratory acidosis and alkalosis. Now, in this case, PCO2 and pH are in opposite directions. And very quickly, again, the important thing that I want you to bear in mind is that we have an acute response, which is where the cells control their buffer levels. And we have the chronic response. And we have the chronic response, which is where the kidney starts to regulate the level of bicarb and hydrogen in the blood. All right, now each of these equations for the acute response in respiratory acidosis, it's just going to be the delta bicarb is equal to 0.1 times the delta PCO2. Okay, the chronic compensation is going to be delta bicarb equals 3.5. Okay, actually, let's simplify the equation down a bit. 0.35 times the delta PCO2. Okay, so this is for respiratory acidosis. Now for alkalosis, our acute compensation is going to be delta HCO3 equals 0.2 times the delta CO2. And for chronic, it's going to be delta bicarb is equal to 0.4 times a delta PCO2. All right, let's not waste any time. Just go straight into the examples. All right, so our example for respiratory acidosis, we are going to have a pH of 7.15, PCO2 is 80, and HCO3 is 22. Okay? So in this case, as you can see, the pH is low and the PCO2 is high. They're in opposite directions, that means it's a respiratory problem. Since the pH is low, that means it's a respiratory acidosis. Now, let's calculate what the expected compensation should be. Now, in this case, we get to be a little bit fancy because we have to do both at the same time and then compare each one to our current bicarb. Okay? So, the first equation is, it's our delta HCO3 equals 0.1 times delta PCO2. All right, so our PCO2 is 80, and just as a reminder, normal should be 40. So 0.1 times delta PCO2, so 80 minus 40 equals 40. So 0.1 times 40, which equals 4. So our delta bicarb in an acute respiratory acidosis should be 4. Okay. Now, as we know from before, our normal bicarbonate is 24. Our normal bicarbonate concentration is 24, and because it's because the bicarb is supposed to compensate, then that means our bicarb should increase to 28 plus minus 2, so 26 to 30. All right, now, this is in the acute case. In the chronic case, you're going to do the same thing, but this time instead of multiplying by 0.1, we are multiplying by 0.35. Okay? So just to do the maths very quickly, times 40. This is going to be 14. And so our expected range is going to be 24 plus 14, which gives us a result of 38. Again, to give you a range, you do plus minus 2, so 36 to 40. Okay? Now, as you can see, in both the acute case and the chronic case, the HCO3 is far too low. Okay, it's below both of these ranges. All right, this tells us that there is a metabolic acidosis on top of our respiratory acidosis. Or in other words, we have an uncompensated respiratory acidosis with a metabolic acidosis. Okay, so let me just take the chronic example. Let me just take the alkalosis example, second example, which is 7.65 PCO2 is going to be 20, HCO3 going to be 17. All right, so our pH is high and our PCO2 is low. They're in opposite directions, so it's a respiratory disorder. pH is high, so it's a respiratory alkalosis. Now, let's calculate the compensation again. Okay, so you guys hopefully will know the equation by the time the exam comes. But first of all, delta PCO2, right? So 40 minus 20, that's going to give us a nice round result of 20. So 20 times 0.2 to find our compensation. In this case, that's going to give us a result of 4. HCO3 so that's our delta bicarb. So in this case, because it's an alkalosis, we expect HCO3 to go down, right? So our total HCO3 should be 24 minus 4, which is 20. Okay, so to give us a range, so 20 plus minus 2, what that means is that our range should be 18 to 22, okay? That's for the acute case. For a chronic respiratory alkalosis, same thing again, but instead of 0.2, it's 0.4. So 0.4 times the delta PCO2 will give us a result of 8. So 24 minus 8 equals 16. 16 plus minus 2 gives us a range of 14 to 18. Now you'll notice that in this case, the bicarb is within range for a chronic disorder, right? And so this tells us that this patient most likely has an appropriate compensation for a chronic respiratory alkalosis. If this case was acute, that would tell us that this compensation is inappropriate, the bicarb is too low, and so they have a respiratory alkalosis, and on top of that, a metabolic alkalosis, metabolic acidosis. Does that sound good? Very quickly before we move on, is everything clear? Does anyone have any questions? Okay, so I guess everything is clear. So, what is the condition? The first case or the second one? Okay, so for the second one, we have a respiratory alkalosis. If I just give you the example a second time. So with our second case, it's a respiratory alkalosis because our pH was high at 7.65. Our PCO2 was 20, which is low. So this tells us that it's a respiratory alkalosis. We used the equations to find. We used the equations to find the compensation, right? And our bicarb was 17. Okay, we used the equations to find the acute and chronic compensation. In the case of acute, our expected HCO3 was 18 to 20, whereas in our chronic, it was 14 to 18. Okay. Now, in this case, you have to actually look at the case scenario itself. If it's telling you that it's an acute condition, if this is a patient that, like, oh, this morning they started to develop a respiratory alkalosis, right? Or, for example, they were given something like morphine, which makes you breathe slower, and so you'll expect a respiratory alkalosis. You want to look at the acute response to see if it's appropriate. If the case is telling you that it's chronic, then you would look at the chronic response. But in our case, because we don't have any numbers, because we don't have a case scenario, we just have the numbers, we do both, right? And so what we will do after we do both equations, we'll say, hey, if this case is a chronic respiratory alkalosis, the response is appropriate. If the case is an acute respiratory alkalosis, then the response is too low, it's inappropriate, and we have a metabolic alkalosis on top of the respiratory alkalosis. Wait. No, we have a respiratory alkalosis, and on top of it, we have a metabolic acidosis. Is that clear? So in our case, we have a respiratory alkalosis. If it's chronic, then it's a chronic compensated respiratory alkalosis. If the case is acute, then it's an uncompensated respiratory alkalosis with metabolic acidosis. Okay, okay, wonderful. Okay, so these are a bunch of examples. These are actually the examples that he used in the lecture. For the sake of time, I don't really think I'm going to be able to go over them today. If there's any particular one that you want me to go through and explain, then that's fine. But other than that, thank you guys so much for attending, and thank you to everyone that made this possible. If there are any questions, I am more than happy to take them. All right.